Because and we talked about that there are actually 3 ways to conduct a hypothesis test, right? We can draw the little diagram, and this is pretty old-fashioned. You know, drawing the little diagram, having the little critical value, and p-value is a lot stronger because we can talk about a probability, right? An established probability. It's not just about reject or not reject. Because that's all we do here. Reject, don't reject. And it becomes really flaky when you can change your alpha and your entire result changes, right? So that's why p-values are more meaty, because they give you more to talk about. They give you strong evidence one way or the other, or not strong evidence one way or the other.
Is there a better way to word the P equals the HO and the H1?
It's just the way it's done.
Okay, so-
What do you suggest?
Well, because like when I read that, and like if I was to do it on a test, and that's how I'm imagining it, like I'd see that and be like, well, you know, it's not asking me for the range, it's asking me specifically, does P equal 0.37? And I know we got something that says it's in between it, but that doesn't necessarily answer whether or not it's right or wrong, in my eyes. Like, well, I understand that there's a good chance that we get something similar, but then shouldn't it be like P is equal to, or P is like a number that's greater than or less than, like it's in between 2 numbers kind of thing? Versus that it's not.
Okay, so here we have something that has been established, okay, and we're given that.
Right.
According to a survey conducted by the American Animal Hospital Association, they were given a fact, okay? So according to their survey, they're saying 37%. So we're saying we have this fact. And somebody comes along and says, I don't believe it.
Okay.
So and then you're using your sample evidence to say, well, you don't have a right to not believe it, or, yeah, you were right. It's
P for proportion.
Yeah,
Right.
so this is population proportion, not p-value. Okay, is the population proportion about 37%? Okay, or is it something significantly different?
Okay.
And the p-hat is the sample value, right? It's the point estimate for the proportion of individuals who really do talk to their pet on the phone or answering machine. Okay?
Okay.
And then p-value is the probability that this is further away from this.
Okay.
Okay? All right, you guys ready? Okay, because we only have 3 classes left, I'm going to jump to 11.1. Okay, so in chapter 11, 10.5 is very, very good practice. I highly recommend it. There's no points associated with it, just like the last section in chapter 9. But it is really good, good stuff. Okay, so in section 11.1, we're starting to talk about 2 groups. So in chapter 10, we've got 1 parameter. Okay, we've got 1 proportion, 1 mean, that has been established as some number. And our hypothesis test involves, is that number correct? Is that number something different in some way? Okay. In chapter 11, you've got 2 groups, and you're comparing them to each other. Okay? 1 parameter, you're comparing it to a number, an established number. 2, you're comparing them to each other. Okay? So in section 11.1, we're talking about a test for dependent, 2 dependent samples. Okay?
Middle lights don't work.
Oh, the middle light is,
Yeah.
flaking on us? Okay. So each of the sections in chapter 11 is a tiny bit different. But at the end of the day, they're all comparing two groups. They're all comparing two groups. Okay, so in 11.1, the samples are dependent. And this happens like if you've got a before or after, or a mother and daughter, or father and son, or brothers, or something something where the two samples have some kind of a connection. Okay? And this process is called matched pairs. And again, it's inference for two dependent samples. Okay? And here it's really important to note that we're testing the differences. You're testing the differences between the two groups. So what you're really testing is, we call it mu d, which is the mean difference. And it would be the difference between mean 1 and mean 2. Okay? The hypotheses. In HO, you're going to have that mu d equals 0. Always 0. And what it means is, guess.
No difference.
No difference. Good. Means there's no difference between the two groups. Versus the alternative, where you're going to have that the difference, there is some kind of difference, or the difference is greater than 0, or that the mean difference is less than 0. Now, let me write this better. Okay. Now, if you're looking at these values, how do you establish this? Okay? If you take a bigger number and subtract a smaller number, what type of number do you have? Positive, right?
Yeah.
It would mean the difference is greater than 0. So that's when mu1 is greater than mu2. Right? Bigger minus smaller. Right? Positive. Greater than 0. You with? Okay? So consequently, if you take a smaller minus bigger, what kind of number? Negative. Perfect. So if you've got mu d less than 0, it means when mu1 is less than mu2. Because again, you're looking for that difference. Difference meaning just subtraction. Okay, you guys with me? Good. So you still have the three types of alternative hypotheses. They still determine the type of test. But I do all this in the calculator because it is horrendous calculations. Okay? The test statistic here, let me back up. Yeah, the calculations in chapter 11 are horrendous. I don't do any of them by hand. Okay? No critical value junk. Nothing. No even calculating your confidence intervals by hand. They're awful. Awful. In some cases, just finding the degrees of freedom would take you half an hour. Seriously, it's nasty. Okay, so, where was I? Oh, the assumptions. The assumptions are that each, no, let me back up. The assumptions are that the differences are normally distributed. that would be that, those numbers that you get as a result of the subtraction. So you're going to take, let's say you've got sample 1. So you've got x1, x2, x3, x4, right? There's all your data, okay? And let's say you have sample 2. And let's say sample 2 is y1, y2, y3, y4, and so on and so forth. Those are the pieces of data, okay? So the thing you're actually testing are the differences. So your actual data isn't the data from sample 1 or the data from sample 2. It's x1 minus y1. x2 minus y2. You with me?
Yes.
x3 minus y3. So you can see where the calculations here are pain. So the data here, these differences have got to be normally distributed. You usually have a small sample, which means that you have to look at a normal probability plot, or you got to have 30 or more differences. Test statistic. The test statistic is a t-value, right? It is a t-value. So the differences follow the t-distribution, and it's because we assume that neither standard deviation is known. Which is usually the case. And if, I'm not sure, even if we knew the standard deviations of the populations of each value, I think it would still fall under a t-distribution because you're looking for again, your data is not sample 1 or sample 2. Again, it's those differences. So I think it would just follow a t-distribution anyway. So your test statistic is a t-value, and it is d bar, which is the mean of the differences. These are the d's. So this would be like d1, d2, d3, etc. Oh, there it goes. Look, there be light. Divided by the standard deviation of the d's over root n. And that has n minus 1 degrees of freedom. Okay? A confidence interval is similar. For the mean difference, it's d bar minus some t-value times the standard deviation of the differences, I think, isn't that it? Over root n, excuse me. To d bar, so that's just the mean d, like x bar, right, is the mean of the x's. This is just the mean of the d's. Okay? Plus t of alpha over 2 times the standard deviation of the d's divided by root n. Okay, so it's a lot easier than it seems. It's just a t-test and a t-interval. And although you're looking at 2 groups, you're testing one statistic, which is these d's. Does that make sense?
Yeah.
But wrapped up in these d's are both samples. Okay? So you're testing 1 but 2.
Yeah.
2 rolled into 1. 2 groups rolled into 1.